talk, obviously, is going to be on buffer overflows on the SPARC. You were just treated to a great talk on basically advanced techniques you can do. I'm going to try and focus on this, on doing overflows on other architectures, most notably the SPARC. The SPARC, for those who are unfamiliar, or probably have just heard of them, is... Oh, well, this is what I'm going to talk about. Sorry, I'll get out of order. I'm going to do a crash course on the SPARC and SPARC assembly. Just because I'm going to focus a lot on writing the shell code or the payload, because that's what differs the most between Intel and the SPARC. And a lot of the techniques that was already talked about how to deliver the shell code equally applies here. There are some little nuances that'll make it different, but as a general conceptual overview, it's the same. The stack is much funkier on the SPARC, and I'll make sure I cover that. I'll cover some of the tools that I'm using to develop the shell code, and as examples, I'll be doing everything on a Solaris box, this one right here. And Solaris is so nice to come with a wonderful debugger. ADB is called the absolute debugger, is an assembly language level debugger. So you can step through, look at the registers, look at, patch binaries, you can patch values in memory, and do things a lot easier than you can with GDB. And I will speak up as everyone is motioning towards me to do. Then I'll discuss exactly what happens on an overflow, and start discussing shellcode and some methods of delivery. And I'll be giving some examples too, because I like doing that. Okay, the SPARC, standing for Scalable Processor Architecture, created by Sun in the early 80s, was based on the RISC designs out of UC Berkeley, and basically the whole philosophy was make the chip as simple as possible so it's blazing fast. And part of what this is a 32-bit wide path. Everything in SPARC is really pretty because every instruction is 32 bits wide. Your shellcode is nice and square. It's really fun. It makes things just typically easier for calculating the size of your shellcode and calculating jump addresses and stuff like that. It's a pipelined architecture, which I just had to mention because it will get you in some places. Every clock cycle, it basically executes 1.5-ish instructions, where it basically prepares the second instruction. So you have to watch out when you're branching that when you branch, jump to another location in code, you will execute the statement after the branch. So just keep that in mind when you're writing your stuff. Part of the other things to speed this up is the load store architecture. All logical and arithmetic instructions only operate on the registers. You can't fetch things. You can't just increment something in memory because that would involve making the chip smarter and slower. And the one thing unique to the SPARC is this wacky invention called register windows, which I will cover in great depth because it's kind of crazy. In memory access, basically, it's relatively simple. The only instructions that can access memory are load and store, and that whole family of instructions: load by byte, load by half word, so on and so on. And all memory access is register indirect, meaning that you have to write something in the value contained in a register, whereas each register acts like a pointer, basically, as they would in C. So this chip was actually written for C compilers, so it does. If you think in C, the SPARC will be very nice to you. All instructions are one word. Very nice. The registers. RISC chips always have tons of registers, which make things really easy. At each given point in time, you have access to 32 registers. The chip may actually have more registers than that, more general-purpose integer registers, but you can only see 32 of them at a time because of the register windows, which I'll talk about. You always have the global registers. You have 8 of them that are accessible across every function. You have the output registers, which you load up the arguments to a function to be calling. You have the local registers, which are local to your subroutine. The inputs, which are your caller's output registers. Things to note: the output register 6 is the stack pointer. That points to the bottom of your stack, bottom being the lowest memory address. The input 6 is the frame pointer, which is your caller's stack pointer, and also it points to the top of your stack space. How register windows work is it's a circular stack of 16 registers, the inputs or the outputs and the locals, which are rotated among functions, so you don't have to worry about pushing arguments onto the stack or so on, and to speed up function calls because it was written for C, and that's what you do all the time. The caller's output registers become the input registers in the next function, and these are all handled by the save and restore instructions. The save and restore instructions allocate your new register set, and they also allocate the stack on the space, or the space on the stack, which we will. Oh, we have to get the subroutine calling conventions. Basically, to call a subroutine, very simple. You just place the arguments in the output registers. You use the call instruction to actually jump to the location in memory containing the code for the function. The callee uses the save instruction to allocate a register window, and will also allocate their stack frame. And with that, they calculate the minimum space they need for the stack, in addition to anything they need for local variables. And it's all allocated in one instruction. Interesting thing to note is that when you are allocating space on the stack for the register window, they're not actually written there. They're only written there when the system runs out of register windows, and when that happens, a trap is called that signals the operating system that it needs to flush some of these registers out to the memory stack. And so basically what you're doing is you're saying, when you need to dump them here. So you're not actually guaranteed to have them written there, which is kind of difficult because the point of overflowing the buffer is to overwrite the return address. But if the return address is in a register, you have complications. And the callee does its thing, and at the end it does a ret, which is return to the caller, which just basically jumps to the value stored in the input 7 register plus 8, because the 8 is added because of the register the branch delay slot that when it's called, it executes that instruction and the next instruction, so it has to go 8 back. Simple example, we have our main just will call the function foo, and we'll set the output register 0 to dead beef. This is executed because it is in the branch delay slot. Control transfers over to foo, which saves. The save instruction is interesting because the first argument, one thing to note about SPARC assembly is the destination is always on the right. So it was save starting at the original stack pointer and decrement the stack pointer by 96 bytes, which is the minimum stack frame needed to dump the registers, and store that value as the new stack pointer. And in between those is when the register window is rotated. So the value of the stack pointer, the first operand, is now in the frame pointer register. Then it just loads the value stored at the memory address stored in register input 0 and puts that value in register local 0, adds 42 to it, storing the result in register local 1, and similarly stores the result back in dead beef. Then it returns, and return just transfers the control back, and because of the branch delay slot, the restore flips the register window back and deallocates the stack. So when transfer is controlled back, the caller thinks the world is right again. I want to define traps for you. These are typically called interrupts in other operating systems and architectures. They are transfers of control to supervisor software, meaning it's a request from the application or from other supervisor code or from the actual hardware for the operating system to get up and do something. These are handled for window overflow and underflow conditions where the operating system has to dump them to the memory stack or restore them. The question is, why do we care? System calls. If you're familiar with Unix kernels, they are all based upon having tons of system calls that will do everything for you. These are all in the man section, the manual pages, section 2. Open, close, exec, fork, all these fun things are all there for you. To make a system call, all you do is look up in syscall.h the system call number of the system call you want to execute, throw that in global 1, and execute trap 8. Simple example here. We are going to set the output register to 0 because global 0 is basically the dev null register. It's hard-coded 0. 23 is the index of the set UID system call. Move that to global 1, do the trap. Notice there is no branch delay slot after a trap. It's only on branches and calls. Now we'll just execute set UID 0, which we'll see why we need to do that soon. The stack. Like other architectures, the stack goes downward, and it reserves the space for the window in case of overflow or underflow. And basically, in a well-behaved, convention-obeying functions, all automatic variables are referenced by negative offsets from the frame pointer, because, as my little art in the next slide will show you, the first part of the stack in the higher memory address is the space, if any, for automatic variables, so you just index them that way. And then the bottom of the stack is stuff for the register windows. But you actually really don't need to reference those, because nothing is guaranteed to be there, so why would you want to do that? And here's basically a struct representation of the minimum stack frame. And they do some interesting stuff here. You have 8 words allotted for the local registers. Then you have 6 for the input registers. And notice these 2 are also the input registers. We have the frame pointer and the saved program counter, which is where we'll be jumping back to. So basically you have the 8 locals, and those next 3 lines form the 8 inputs, which means you can only pass 6 arguments through the registers to a function. Then we have the structure return address for returning compound values. They decided to throw that in there for fun. So you could store a pointer on the stack instead of putting in a register. I'm not sure why. And then we have the argument dump area, which is so that the function being called, if it so chooses, can dump its arguments that it got on its input registers onto its stack. Okay. If you need more registers, you can do that and get them all. And then we have the argx area. This is the argument extension. For more than 6 arguments to a function, this space just kind of grows as far as needed to place the arguments there. This is allotted with the caller's save instruction. You put those in there, they load them in. The function will know to reference them as negative to the frame pointer, as yes. And that's how that works. We won't really be using that. But here's a nice ASCII art depiction of the stack. Stack goes this way, and I have it going left to right just so you can read it and you can see the string buffers as they are. Locals, inputs, the structure, return address pointer, or the instruction pointer. The argument dump area is 24 bytes. I have the sizes used by them up there. The argument dump area is that 1 byte. Is also sometimes referred to as the hidden word, which is used to make sure that the stack is double word aligned. The stack and the saved program counter must always be double word aligned, or else your chip will get very angry with you. And we're going to make it very angry, but not so angry that it barfs. And then automatic variables we stored here. Like right here in my example, I have a string pointer called buff of indeterminate size. Doesn't really matter. And then we have the frame pointer, which is the boundary between our caller's stack frame. There are his locals, his inputs, and where that little asterisk is, that's his saved program counter. That's our target. That's what we need to hit. And it's pretty easy to see that if the buffer grows outside of its boundaries, you just overwrite his registers and just basically take him over. Which actually presents the interesting thing is you're not overflowing and taking over the function that with the fixed length buffer in it. You are overflowing and taking control from his caller, which is very interesting because sometimes your caller can call the overflowable function, return, call another function, which will overwrite your wonderful stack frame and shellcode, and then basically you're screwed. But of course, you just attended the Greg Hoagland's talk on how to do cool things with the stack and where you can put the code, and so something like that should not be a problem. But this is what's going to happen when we are overflowing the buffer. I'm just going to trace through over how the register windows rotate the registers and how things change. Obviously, the previous stack frame's saved program counter is overwritten, as is all his other registers. The function returns his his frame pointer becomes the target address, and his input 7 register becomes the target address also. And the stack pointer is still valid. The stack pointer will still be the pointer to his stack, which has not been totally foobarred at this point. All his values that he assumed to be safe have just been totally messed up, so he just freaks out, hopefully getting an error condition immediately and returning. And if he does, he tries to jump to the input 7 plus 8, our target address plus 8 bytes, and that is where we would take over control. This is your stack on drugs. Basically, we have all these registers, or these areas on the stack are fine, and at our buff, we just overflow and write our target address off into the horizon as far, you can basically write it as far as you want because nothing's going to behave well at this point. Yes? Oh, thank you for reminding me. Okay, basically we were told that we are not guaranteed that these values will be there. But what happens is, basically, implementations of the SPARC architecture, as it's an open architecture, are allowed to have anywhere from, I think, 8 to 40 register windows. Luckily, those register windows are always filled, even like in the lowest stages of the kernel, so you can basically assume that every time we do a save or restore, they will be restored from the stack, or saved to the stack and restored from the stack. So that when the overflowed function does a restore, we'll assume that it's the registers that thought it had in the register window had become, were written to the stack, and so it restores them from the caller's stack. So basically what it does is we have our target address written all the way through there, and it just loads up its registers as it transfers control to the caller, loads up its registers with the target address. I will do some examples and I'll show you what this looks like. Stepping through the program, and you'll see all the registers are just totally just spammed over. One of the very nice tools that Solaris comes with is just a disassembler. If you ever looked into basically writing the shell code, writing the assembly code, and then changing it to the bytes, it's a pain in the butt. But this makes it rather easy, especially when you just throw a Perl script on top of it, and it's a nice little chug, and you have a nice little header file that you can use. There are freeware SPARC disassemblers available. I just found a page about 2 hours ago off linuxassembly.org, has a link to an NetBSD, link to some SPARC assembly examples, and on this guy's page he has his own SPARC disassembler and SPARC assembler and a couple others that you could use for Linux and or BSD, all running on SPARC, of course. Excuse me? Is it free? Is it free? Oh, very nice. Okay. Well, if I'm sure we can find that. If you want to give me the URL, I can throw it on here for people. Oh, I forgot who already, but someone has a really good free disassembler. GNU? There's a GNU disassembler? Oh, wow. I was unaware that they had a disassembler. Wow. I have done my research. Okay. And the other tool that we'll be using extensively is the Absolute Debugger. Because this thing, correct me if I'm wrong again, I have not seen anything like this for any of the free operating systems. They tend to use GDB for their kernel debuggers and everything else, but I have not seen something that is as assembly language as this one is, as assembly level. Rather funky syntax to get used to if you're coming from the world of nice and pretty hand-holding debuggers. Arguments are address, how many iterations to do, and command and modifiers, as you can see. First instruction, it says starting at the address of main, in the object file. The question mark means in the object file. The slash means in the memory image, whether it be a core file or the actual memory of the running process. What I'm saying on the first one is dump 10 instructions, or disassemble 10 instructions starting at main. One of the wonderful idiosyncrasies of this program is everything on this side of the question mark or slash is in hex. Everything on that side is in decimal. But there are modifiers you can use to put them either way, but we should all be very fluid with conversions, even though I'm not. The second example, just display the word stored at CodeBabe. That's not a real address, but I like it. We can also just query individual registers. Basically, you have like a pseudo redirection instruction that'll say, give me the address of the stack pointer, assign it to the variable x, and it'll print it out for you. The next instruction says, display 24 words starting at the stack pointer. That will give you the full minimum stack frame. And then from there, you can, after that point, will be automatic variables, if any, but every function must have at least those, and you can check them out. Here's a more interesting one. In the address of the frame pointer plus 3C, which I can't remember. I'm on the spot, so I can't do math. But that will be the saved program counter. Write the value dead beef. And so then you just write the value, step through, and you'll see the program try and jump to it, or see the caller try and jump to it when it becomes time. The ADB will also do interactive debugging, some simple stuff like this. So you don't really, it's not really pertinent, but I threw it on there because I needed space. Wow, this is very difficult to see. This is a contrived session of using ADB to examine what happens when we overflow a program. I wrote a simple program called Smash Me, which I'll show you in a couple of minutes. That basically just does the fatal flaw. Does a stir copy or a stircat into a fixed length buffer. And it just takes the argument on the command line, so I'm just saying run it with this argument. And I said first to set the break. Oh, there also is no prompt in ADB, so it's kind of hard to follow along. I said smash :b means set a breakpoint at the smash function, which is I have main and that calls smash, which has the overflow. And then we run it with that argument. Stops at the beginning of smash. We're stepping through, allocate our stack pointer, and we're going to store the value, go through. We're just stepping through, watching it. It's going to call, I think, right there at the bottom of your screen is where it calls stircat. But right now we're going to watch. I can't remember how I did this. Oh yes, I call stircat. But first I look at our stack pointer and I look at the frame pointer, our caller stack frame, and then I step over that instruction, which will call stircat, and we're going to watch what happens after that. The :E means step to the next instruction, but don't follow any jumps or any jumps or calls. As you can see, the saved program counter is overwritten, as is his entire stack frame. He is not happy. And then I basically just step through to the end, and I go right here to where he returns. And so when he returns, the stuff stored on his stack is loaded off the stack into registers, and then using the restore instruction is flipped over to his caller's local and output registers. And so now we have them all loaded in, back in control of main. They're all loaded in there. And we're going to step through the last instructions of main where it tries to do a return right here. And it says a bus error because the address 41414141 is not aligned. And you'll get that. It's a nice way just to see when you've messed up. Quit out of that. I'll run through that again later with another real-world example. I'm going to start talking now about how to write assembler code that we'll use as mobile code, position-independent code. We can just throw in there and it'll just execute on its own behalf and take control of the process. Basic two ways to write this is using your compiler, you can make a ASM block, which basically just says, this is straight assembly code, and you just write it in there, compile the program, you run it, and if it gives you a shell, you obviously know it's working. And then after that, I throw the function into a character array, and then I cast that array to a function pointer, execute the function pointer as the final stress test. Here's my first example of some SPARC shellcode. This is somewhat brain dead in some ways, which I'll explain. So like this representation does contain null bytes in it, so there it's useless basically, but it's ordered in a simplish way to show you just how we're going to write it. I think I write my shellcode at first as if it's a well-behaved function, so I allocate in a new register window, and I just basically I'm calling exec, so I'm creating the character array of the function to execute, and I'm creating the arg value, the arg vector. Throw that in there. And I'm just giving it a null for the environment pointer because who cares? It'll be messy, but it's not a problem. One very handy thing about the SPARC is that it's big endian, and so you can write strings in a relatively straightforward way, just straight to the stack. One way to do this is if you're lazy, most of the Unixes will come with the octal dump program, and if you just do echo string pipe octal dump /x for give me hexadecimal output, it'll give you a nice hex, and you just basically just chop it into words and start storing them on the stack, and you have a string. I'm sure there are ways to do the cool little jumping thing that will actually load the address of the string, so you can just write it straight, but that's a little over the top for now. Yeah, and you can basically see I set 59 to the system call number, execute the system call. This can basically be looked at as a well-behaved function to just exec a shell. Then I chop it down a little more. It doesn't assume it's a well-behaved function. I am lying on that second line. Ignore that. Basically, I chop out the save and restores, and I just start using the current stack pointer, because in the situation where the overflow occurs, assuming the well-behaved function assumes that you have valid stack pointers and frame pointers. You can get in situations where your stack pointer will be pointing to right behind your code, and as you're storing memory, you'll be chasing your code as your code executes, and you're overwriting behind it, and you don't want to be there. So this code also will not work because it assumes that the frame pointer is valid, but as I discussed before, the frame pointer will be the target address, and so you're stepping on your toes here. But this is another example of just chopping things down. You can see I set here. I'm going to explain the string more. I set the 2 words and 2 following registers to a store double word instruction, starting at the address of the frame pointer -16, so it writes the full 8-byte value down. And I basically am constructing in memory the string followed by a null, so that I can use it for both the name of the program to execute, and I build a pointer to that array of character pointers to use as the arg vector. If you've seen Aleph1's code in the Smashing the Stack for Fun and Profit, he does this also. Very easy and straightforward way to do it. Here is my even better shellcode. I'm not saying it's really great, but in writing this, there's an interesting caveat that is not addressed in Smashing the Stack for Fun and Profit. Under System V systems, the shell, the bourne shell /binsh, when past an effective UID of less than 100, will discard it. So that effective UID is triggered when the program has the SUID bit set, which means it keeps your real user ID saying this is who you really are, but effectively your root. And then it calls the shell, and the shell discards the effective UID, and so basically you found that you've exploited a SUID program, and you still have your own privileges, and you're not very pleased. Yes. The second one, it contains a null byte in this. Oh, thank you. Okay, the set is a synthetic instruction, meaning the assembler basically expands it for you. And the set, because everything is 32 bits, how can you write a 32-bit value in the instruction? Because it splits it into 2. It first uses the set high instruction to write the highest order 13 bits to the register, and then does an OR with the lower 13 bits, or the lower 8 bits to complete the whole value. And we'll see when I disassemble the shellcode how it's changed over. And I'm just lazy, so I just do the set, because it's easier to see the string there instead of 2 words. But yeah, that will eliminate the null byte. The null byte will still be in the set, in the OR, but because of the way that the opcode for OR is aligned with the bits, it will not be on the correct boundaries to be in fact, null byte. It'll be spread across. Don't have a diagram of that, but you can take my word for it, or call me a liar and chase me out to the parking lot. It's your choice. Let's see, nothing else really change here. Oh, you'll notice that I do not trust the frame pointer anymore, because I've stepped through with the assembly debugger and I'm like, wait, why am I doing that? That is just whack. And so you do everything relative to the stack pointer. I waste 4 bytes before the stack pointer because storing straight to the stack pointer introduces a null byte. And you'll notice when I'm trying to set a register to 0, I can't use the straightforward instruction by just setting to 0 or moving the global register over because that introduces a null byte. So you just do something like, XORs, or there's 1,000 different creative ways you can do that just to feel fun. I'm just going to talk a little bit about the delivery, but not that much because it has basically been treated well better than I could by Greg Hoagland. Same on other architectures. You need to do the no-op sled and then the shellcode, and then write the jump address off into infinity and let it jump back, which has the problem of if the caller of the overflowable function calls another function, you're not necessarily toast, you're just basically dodging bullets. Or you can just write the jump address to overwrite the saved program counter, then put the no-ops after it and the code after it. So basically you're jumping backwards in the stack to the caller of the overflowable function, the meta caller in this case. And basically, because the register will be, the saved program counter will be borked by that point, you won't have to worry about those stack frames. They can just go to hell. Greg Hoagland talked a lot about this. Very well, I might add. Okay, some real-world examples if I can find a place to put this microphone. Okay. Can everyone see the shell? Okay. All right, looks good. Examples. Okay, first we're going to have our nice little simple smash me example. Here's the source code for that. Very, very simple. Smash with the argv1 stircat to a 128-byte buffer. Now we're going to meta smash me, which will smash me. One thing you'll basically always see is the calling function will get the value of its stack pointer because it calculate the offset from its stack pointer, so it can try and guess the stack pointer of the function it's trying to overflow, because there'll always be a defined number of bytes down the stack, a certain number of function calls down the stack. And so basically what you're going to be doing is you're just going to be creating a very large string. In this program, what I do is I write, I pass in the argument of the buffer size that I'm trying to overflow. And so what I do is I write no ops all the way up to where the shellcode must fit, then write the shellcode so it's all within the buffer, and then just write tons of return addresses. And the return address is calculated as an offset from the stack pointer of the meta smash me process. So I just calculate the egg size, and it kind of just tells you what it's doing. And it writes, like the no-op I have here is, I cannot remember what instruction that is. Just trust me that it's basically an instruction that does nothing, essentially. and just copy the memory into to the egg. And so the egg represents the entire string I'm trying to pass it with, and I call the function. So let's see what happens if we say the offset is 0. Notice that the shell code I'm using in this example is 64 bytes, so we'll have 64 bytes of null codes, of no ops, and then this shell code. So we don't have that big of a window. It's not happy. So fire up our debugger, with meta smash me, smash me, and the core, legal instructions, got the registers. Notice how the registers are just basically splatted, and so we can just check out our frame pointers, see what they point to. They point to themselves again, because basically I did not go back far enough in the stack where I'm just pointing back at my target address. So let's see, minus 500 hex, notice. That is well beyond it. Okay, so what I'm going to do is, where am I? Look at my shell code. Actually, no, I'll look at my no op. I'll see that byte there, and basically I'm going to search through memory for where that thing is, and that'll basically calculate the offset for me. So I'm going to say we'll start at 500 hex bytes down the stack from the frame pointer, do a search for the 32-bit value. All right. Okay. Search for that value. Shows me where the first occurrence of it is. And now I'm going to do my poor man's X calculator. Is that the value we want? 980. So that right there is our offset. So let's quit out of that and let's put GDB to the test. I'm going to smash me 128 bytes. Go back. We have a shell. We basically landed exactly at the first no op. Thank you. But that's some precision that we don't really need. Basically, we know that we have 64 bytes, so basically we only have to be within 50 bytes or so. So we can just go back and go, try 1,000. No, not happy. 1,050. Bingo. And so the larger the buffer is, basically, the more leeway you have, which we'll go and we'll see my libc example. This is old. This was discovered by Onion, I think, in September 1998 or somewhere like that, and Sun took about a year to post a fix for it. But so I just took all the patches off my system. I'm feeling kind of vulnerable right now, but it's for the greater good. The details of this bug are there's an overflow in libc in its parsing of the LC messages environment variable, where you can overflow that, and basically so any SUID program becomes vulnerable to it. So here's my little program right here. I just ask what program to call, how big the buffer is, and what the offset is. And I'll show you the program in a second. Pretty much the same thing as the last one. Just throws in an environment. You will have to basically write a program to exploit each one you're going for, typically, just so you can customize it, but it's not that big of a deal. And what we can do is we can then, I'm just going to try, let's go for bin rsh, and I basically went through with Perl and basically kept giving larger buffers in LC messages until I got one that died. It was somewhere around 1,000 bytes. That's what I'm going to assume the size of the buffer is. So with offset 0. It dies. Okay. Well, I know now that because it is 1,000 bytes of no ops, or 1,000 minus 64, I have a very gaping large window. And so I'm just going to try by offsets of 500. No. there we go. And that basically gives me a root shell because in the shell code that I'm using, I made sure to call setuid 0 before executing bin shell, so bin shell is happy and trusts me. And it's basically like that. I can use any suid program on the system at this point. So let's do find user bin. Okay, anyone have a favorite? I'll do bin password because that one's nice and easy. But I basically just sat down today and decided which ones I could get, and basically some of these didn't have the overflow in them because they didn't use the locale support in libc to use it, but the vast majority of them did. So let's start with password. And oh wow, looks like they don't go very far down on the stack, and they make it really easy for us. Let's see. What else do I have that's really fun to show you? Okay, let's go for some really cool shellcode that mostly works. I spent the last couple days on this. Strange bug. It's driving me nuts. But here's an alternate way to develop shellcode instead of using the ASM blocks. Just write the assembly file and basically you throw it through the assembler, create the object file, and then I have a main function in a C program that just calls this function, bind shell, and that's just a simple way for me to test it so I can go through here, and mostly because the ASM block just makes Emacs go hairy, and I like Emacs, so don't throw anything. Okay, what I'm doing, let's see, where's the source for this originally? First, I wrote basically what I want to do in C. Create a socket, set it up, bind it, listen, accept the first connection, dupe the file descriptors for standard in, standard out, standard error to the socket, and run bin shell. And I just kind of went through. Translated this into assembly because everything is just a system call. So I do a trap. Let's see. Right there is the socket call. By 230, just look through. The higher numbered ones will change from system to system, so you'll have to look them up if you're doing it on Linux or BSD on there. Just straightforward assembly programming, basically. Going through, go bind, store it all, yada yada. You compiling and I just inserted my standard shell code right there. Using the compiler to output assembly code will be very helpful in figuring out how the compiler does stuff, but it is deceptive in a lot of ways because the compiler doesn't like telling you, or in the various libraries, that it's just doing system calls for all these, so you'll go through like 6 different layered functions, _ socket _ capital U, that'll finally say, oh, I just do a trap. But just to look through syscall.h and you'll see what it really does. It'll get angry at you. But we tested. I just compiled it and linked the two things together. That's the bug. For some reason, when I run it straight, it decides that it will not block and wait for an accept. It'll just kind of do something, and the thread will just continue on and execute the shell. But when I run it through the debugger and say, what's it called, bind shell break, and I run it, and I say, yeah, continue. Oh, no. And I just told it to bind to localhost port 2000. Yes, keep going. It likes to say, I'm about to exec something and things will change, so I'll stop for you, but just ignore that. And basically we have a very mutated, very ugly environmented shell right here. Like it says not found, colon. And you can get enough done from here to do what you need to do. And obviously it's running as me because I just ran it from the command line, but you just basically, through the things I've showed you, convert it to shell code and throw it in the process, and you'll have a bind shell. To do so, I have a nice little here. Just to help me out with writing these, I made my dist2h, and so if I go through to my code, let's see, what I do is I write 3.c, test it out in there. Then I disassemble it to I disassemble it to 3.dis, which says diff main 3. Little noise at the top, so I just chop those off till I just have the disassembled code. Shouldn't hurt you to cut out 3 lines. Not with the script to do everything for you. And then just simple, like, filter. You could do this in Perl, do this in whatever you want, but I did it in C because it's fun. 3.dis, pipe to that, and gives you a nice little header file to include. And this is a quick way to check for null bytes and just look at your code hand side by side and feel warm and fuzzy. But basically, with just a couple little tools, you can just tinker around with writing shell code and stuff, and then amazingly you will wake up and say, wait a minute, I'm actually decent at assembly programming now. This is useful. To be the example, I didn't do well in my assembly class until I started doing this stuff, and of course the semester had ended, then now I know everything and didn't pay attention in class anyway. So, no, grades mean nothing. I don't think I have anything else to show you, and I think I'm out of time. Yeah, show you all those. Oh yes, some links to useful things. LinuxAssembly.org obviously focuses on Linux and Intel architecture, but they have some great info on there on it'll stray from the beaten path and show you some SPARC stuff, some BSD stuff. They have a nice little suite of basically the bin util, or a lot of the smaller utilities written in assembly. So your standard 100K executable is now like 3K because all they do is call the traps themselves. It's not portable, but it's really small and useful for boot disks. Shellcode.org, I just come across either BugTrack or vulndev, some mailing list today. Currently down, we'll have a lot of resources to various shell codes for various operating systems. FRAC55 has a really nice article about writing shell code on MIPS under IRIX. MIPS also being another of the pioneering RISC chips. Very similar to this. It's a very good read also. And this stuff eventually will be on dopesquad.net/security whenever I finish it up and put it up there. So you can look there, but if you see a 404, don't have a heart attack.